Okay, so here we go. Okay, it's a new idea. This problem is asking us to use limits to show whether or not the function has a left half horizontal asymptote. What that means is, it goes back to the fundamentals again. Think of yourself having a table. So I'm not solving the problem right now. I'm just illustrating the big idea. As always, if you understand the big idea, the steps you use to solve the problem are much, much easier. So the big idea is, we have a table of xy pairs. We're supposed to figure out that if the xy pairs became increasingly negative, like maybe we had an xy pair of x of -1, and maybe negative 1,000, negative 1,000,000, something like that, and the x values simply became increasingly negative, what would the y values do? We're wondering what happens here to these y values as x becomes increasingly negative. That's what it means to find a left half horizontal asymptote. Questions on that idea? In a previous class, they may have called it end behavior. You're just looking at the xy pairs, looking at when the x becomes very, very negative. In our class, you need to make a flashcard that says this. So the flashcard should have the blue on one side and the red on the other, indicating how you find a left half horizontal asymptote. You find that asymptote by finding a limit as x approaches negative infinity. Questions about anything? Anything bothering anyone? And if you want to make another card, you can. I personally probably wouldn't. When I saw this card, I would just remind myself that, oh, okay, so if it's a right half horizontal asymptote, that's just a limit as x approaches positive infinity. So nearly identical idea. So to me, I could probably get by with just remembering one card, and the other one would just come to my mind. But if you want to make a second card, you're welcome to do that. So, cool. Next thing. Okay, so we know what we're supposed to do. We're supposed to find a limit. So we can erase this. And I would now write this on your paper as part of your solution. You're finding the limit as x approaches negative infinity of this function called f. Okay, another flashcard. Don't think I've given you this one yet either. So I have found this card to be extremely useful on the AP test. About 7% of all points are going to come from limit questions. And every time I encounter a limit question on the AP test, I remember this card. I would put on the front how to find a limit. So on the front, how to find a limit. And then on the back, you put those 4 steps. So front side is how to find a limit. Back would be those 4 items. All right, first step says if x is approaching infinity. The same rule applies if x is approaching negative infinity. So whether you need that note or not kind of depends on the student. I don't really struggle with that. I know it applies to both. So I'm going to compare terms that add. A term is a part of an expression that is being added to another part. So saying terms that add is definitely redundant, but I leave it in there because I've had students who struggle to remember that the word term refers to things they're adding. Had a student several years ago, her name was Amanda Lindstrom. She struggled with that, and so she finally clicked in her head, so she made a little sign. It's a little hard to see because of the glare, but she said a term was a thing plus a thing plus a thing. Just kind of a simple idea. So when I look up here, the numerator has two terms. There's this blue term, and that's being added. I think it's best to think of a hidden plus sign to this green term. And then in the denominator, similarly, we have a yellow term. That's being added to this, we'll say blue. Well, we already used blue. We'll go red. This red term, negative 8x, which is being added to this purple term, negative 1. So that's what we mean by terms that are adding. But terms are always adding, so again, that's kind of redundant. Questions about anything? Okay, here's what we mean by compare. We'll get Charlie to help me here for a minute. And some points. So Charlie, we look at the red term added to the purple term. The negative 8x is going to change every time we pick a different x. So if we had x values and we're adding them, we're taking negative 8x and we're adding that to a negative 1. Every time we pick a different x, the 8x portion of this sum will change. The negative 1 won't change. So we get some sort of pattern like this. So let's see, total here. This would be 8, that'd be 7. This would be, interesting, 7,999. And then if we keep going, we're going to see something very similar. So the question, Charlie, is this. As the red term is added to the purple term, for values of x that aren't very large, I would say both terms make some sort of significant contribution to the total of the two terms. But as x becomes increasingly negative, which of those two terms? Like, do they both continue to make kind of an equal contribution, or does one make a much more significant contribution than the other?
The red one makes a bigger contribution.
The red one makes a bigger contribution, 3 points for Charlie. And as x becomes more and more negative, that contribution becomes increasingly more significant. So the more negative x is, the less important the negative 1 becomes. Questions? This is what we mean by compare. You're comparing terms that are adding, and you're coming to the conclusion that as you let x become more and more negative, the purple term becomes less and less important. Questions? Oh, Ava, please.
What about before x?
So we'll go to that one in a second. That's perfect. So you okay with keep talking, Ava?
Do you work
Oh,
right to the left?
it doesn't really matter. I just kind of picked two and started talking about them, and now we'll pick two others. Good so far?
And then, sorry.
You're good.
Do you only do things that are in the same denominator or?
Oh, I'll get you to answer that yourself. So, Ava, is the blue term being added to the purple term. No, so you would never compare them. So you're only comparing terms that are adding together. Did that make sense? Yeah, so I won't ever compare a term on the numerator with a term on the denominator as far as adding, because they're not adding. Good question. Good. Anyone, keep asking. Oh, please.
Do we need to write that down anywhere, like that negative 8x makes more of a contribution than negative 1? And if so, how would we use that?
Oh, perfect. 3 points for Laura. I would typically never write any of this. I'm just drawing it out so you have a better ability to see what's going on inside my head. Does that make sense? But I wouldn't write it. Oh, okay. So now we're going to look at the yellow and the red term and do the same kind of exercise. Think of x becoming more and more negative and wondering when those two add together, will the total be dependent upon both terms, or will one term become much more important than the other? And it's hard to do that one by hand, so I did a table here that you can look at in hopes that this would kind of help your memory. So this says n, but think of it as x. N is becoming increasingly negative. Here's negative 5 times n. Shows how that gets bigger and bigger. That's pretty similar to this one here we had, 16. We were dealing with a negative 8x, so not that much different than like a negative 5x. As far as when x becomes very negative, that's going to become very negative. Then we've got that 4x squared. Well, this table shows something being cubed, which will grow faster, but the same idea actually applies to the squared term. The term with the power grows much, much larger, if you look here, than the term without the power. In fact, on this spreadsheet, if you look at this line, when those two are added together, the total is almost completely dependent upon this value. And on the next line, when x goes to negative 100 million, the total no longer has any reference to this value. The number is too big. The computer literally cannot add these two together because this one's too much bigger than this one. And so the computer doesn't even notice this contribution. It's like it's not there. Questions? Okay, so that's what we mean by comparing terms that add. So when we compare these terms in the denominator, we have 3 terms that are adding. And our conclusion is only the yellow term ultimately is going to make any difference. As you let x become more and more negative forever, the red and purple terms become increasingly less and less and less important. And so what we can do is say that the limit of this formula, f of x, is equivalent to a much simpler limit problem. So put an equal. The equal is critical. Make sure you write equal, otherwise you do lose points. This is equal to a different limit problem. Limit as x approaches negative infinity. And on the bottom, we just have 4x squared. It is the only term that really is going to make any difference as x approaches negative infinity as far as the denominator. Questions? Anything bothering anyone? Yeah, please.
Do you need to put the f of x by the limit or not for the second equation?
Say it one more time.
Do you need to put the f of x by the limit for the second equation or not?
Gotcha. 3 points for Juliet. Everyone, and see if you can answer this question. Here's a symbol, f of x. Here's another collection of symbols. And here's another. Oh, let's do one more thing. If we do the same argument in the numerator, the blue term will become dominant. So we can just put an x squared there. X cubed, sorry. the green term will become less and less important as x becomes more and more negative. Back to Juliet's question. So we've got a blue symbol, red symbol, and a green symbol. I'm going to answer your question in a second, Juliet, but I want the class to see if they can do this. Raise your hand if you can tell me, are all three symbols perfectly equivalent? Are they all just different representations of the same thing, or are they different things? Hands up, who knows? All who know. Is the blue symbol mean the exact same thing as the red symbol? Or do they mean different things? And does these two symbols mean the same thing as the green symbol, or do they mean different things? So it's a little harder question than I've asked before, than about half of you. Just need to be able to tell me if they're the same or different. Let's try Henry.
They're the same.
So the blue is the same as the red?
Yes.
Okay, said with confidence.
Yes.
Is the red the same as the green?
Yes.
Okay, Henry says yes. Raise your hand if you agree with Henry. So 2 points, 3 for Henry. Anyone disagree? Talk to me.
We did simplify it, so I think that they're not exactly the same, they're just similar.
Okay, so let's go over that again. So would you say that the blue symbol represents the same or different thing than the red?
I think those are the same.
So let's summarize for the class. Okay, the blue and the red are guaranteed to be the same because the problem says they're equal. So blue and red, absolutely the same. So here, red and green the same. Red and green are not the same formula at all. We literally threw away part of the red to create the green. What we said was, if x is going to go more and more negative forever, then it doesn't really matter whether we use the red or the green. But they are different formulas. This blue here, shouldn't use blue, purple. This purple limit is going to be identical to this purple limit because x is approaching negative infinity. But f of x is not equal to the green formula. It only works because x is approaching negative infinity. So answering Juliet's question, 5 points for Hero. I don't want to put an f of x here. That has 2 problems. One, I'm not really dealing with f anymore. I'm dealing with kind of a condensed version of f. And 2, it's wrong to put a symbol here and a symbol here. You would only need one or the other. So like here, I have the f of x symbol. I don't have the entire formula. Here I have a formula. I don't want to put f of x. Did that answer your question, Juliet?
Yeah.
Okay. Follow-up questions from anyone? Please, Laura.
So putting that like x cubed over 4x squared to the side, it's basically the same as putting it right next to the limit.
Nicely done. Yeah, they give you a little bit of leeway when you're writing it out by hand. They want the x underneath the limit sign. And sometimes you'll see, like when they type it, they'll kind of fit it in here. But when you're writing it by hand, it's okay to kind of put it to the side, like I did. Is this your question, Laura? Kind of like that? Yeah, this purple is identical to this purple here. 3 points for Laura. They're the same thing. Good question. Oh, please, Lauren, sorry.
On the flashcard, it says if x goes to infinity. And on this stuff where we're finding an asymptote, we just know that we are going to infinity. But if it's like a different format for limits, how do we know if it does go to infinity or negative?
Oh, gotcha. For our class, we're going to run into the following kind of scenarios. One, they'll talk about a horizontal asymptote, and you'll remember the flashcard. So yeah, that means limits going to negative or positive infinity. Good with that? Okay. Another scenario would be, Lauren, they might just give you the formula like this. They'll just say, go find the limit as x approaches infinity. So you just read it and do it. Comfortable with that? The third scenario is they might give you a picture, something like this. And then they draw a graph showing the function having a limit as x goes to infinity. Like the values here, as x becomes very negative, these y values are getting close to whatever this y value is here. That's kind of the third way they'll illustrate that they want you doing a limit. Did that answer your question?
So it's going to infinity in all three.
In all three instances, x is specified. Well, x could be anything, but what they're wanting you to do is think about what would happen if x became increasingly negative. It doesn't mean x has to be very negative, because we're still talking about a list of xy pairs, and x could be any number, just depends on what we're trying to analyze. But if they want you thinking about an asymptote, they want you thinking about x becoming very, very negative, or x becoming very, very positive. Not sure if I'm helping.
So, I don't know if this is
Okay,
helpful,
please.
but if it says left horizontal asymptote, then you just go negative, right?
Right, you say, okay, here's where your thinking should begin, Kate. They gave you a formula called F. So your thinking should begin with, hey, that's a list of XY pairs, lots of different ones. I don't know what I'm supposed to do with them yet. They say left horizontal asymptote. Now you say, oh, they don't really want me finding out what's happening with any x. They want me to discover what happens when x becomes increasingly negative. That's simply what it means. And so that's the analysis that you're going to perform. Did that make sense? Lauren?
Yeah,
Doing better? Okay, good. 3 for Kate as well. Anybody else? You're still getting used to kind of my style. I want to get you really, really comfortable with, if like Lauren asks a question, I do my best to kind of answer it. If you still feel kind of foggy, do one of two things. Come see me like before school, lunch, after school, so we can talk in a smaller group, or just speak again and say, still don't get it. And then I'll try to find a different way to say it. So, cool. Back to here. So we have the formula called F, and now we're supposed to find, as I said to Kate, because they asked us to find the left horizontal asymptote, they're telling us to find that black limit. We don't want to find that black limit because that's too complicated. So we're instead going to find this yellow limit here because it's easier. And we got to that point by following this step number 1 on your card. So. Okay, next step. Get a little space here. So I'm going to erase some of these notes. Cool. As I said to Kate, let's see your eyes on this one. Okay, what you do in this class, far less important than how you think. If I get you thinking correctly, even if you're writing it all wrong, it won't. Like, we'll fix that easily. It's when your thinking is kind of following the wrong pattern of thought, then it's a much harder fix. So just keep asking. Like, it really is important that, like I said, when you look at this, you don't think, oh, this means just x is negative. No, x could be anything. They just want you to study what's happening when x is more and more negative. So, okay, next line. The next line is just simple math. We simply have factors that are multiplying here. Factor means things that multiply. So I'm going to write it in a way that makes it easier to see. And you would see this in the back of the packet as well. Because they're multiplying, it's easy to break them up. It's not so easy if they're adding. But if they're multiplying, it's easy. So I just wrote it kind of spread out to make it easier to talk about. Let's get the whole class to raise your hand now. You're trying to think what happens when x becomes increasingly negative. As x becomes increasingly negative, this number is never going to change. It will always be 1/4 because it is not connected to x in any way. It's just 1/4. As x becomes increasingly negative, raise your hand if you can tell me what the value of this blue box will become. Oh, that was good. It was too easy. I shouldn't have said raise your hand. I should have just said say it out loud. The blue box becomes 1. X doesn't become 1. For any x, the blue box is 1. But again, this whole argument is only valid if we're thinking of x becoming very, very negative. So that's 1. Say it out loud. What's 1 times 1 for? 1 more. Okay. This one here, though, as x becomes increasingly negative, that's going to become increasingly negative. So if you were trying to figure out what this thing does, well, as x becomes negative, y becomes negative with it. That's not a horizontal asymptote. This limit is negative infinity. So therefore, f of x has, boy, I could put in the word, no left half, or left hand, I don't know, either way, horizontal asymptote. Question? Oh, please.
Oh, when you're writing that end statement, could you use either of those three, like the therefore or since? Would they both?
The therefore or what?
Or since?
Oh yeah, either way.
Either way.
Oh, good question. They're not real picky on, you could say like this, and then you could just leave off the therefore. I think they'll still be happy. Since, hence, any fool can see, whatever, It doesn't really matter. It's going to be like really arrogant. You're like, well, duh. F of x. Obviously. You have a little freedom there.
Okay, thank you.
Make the grader laugh, I don't care. Please.
So if this kind of goes back to what we were talking about before, but if the like x cubed over 4x squared formula doesn't actually equal the one that's boxed in red, why do you write an equal sign at the beginning of the, that one?
Outstanding. Ticket for this one. No, really, look up. Look up. So I'm going to get you to summarize it, Henry, just to help again. So, Henry, is this symbol right here perfectly equal to the red symbol?
Yes.
Yeah, they tell us that it is. So f is that formula. We're trying to find the limit of f because we know we're trying to find the horizontal asymptote. But finding the limit of f would be equivalent to finding the limit of something like I could come over here and put another equal sign and say this is the same as finding the limit as x approaches negative infinity. Henry's getting a full ticket because it really is a crucial thing to understand. It should be simple once you see it, and it should not be hard to remember, but I can't let you leave the room if you don't see it. Like knowing what's truly equal and what isn't is essential. So this black limit is identical to this limit because this, Henry just said, this blue formula is identical to this red formula. Are you comfortable with that, Henry?
Yeah.
Anybody have a question to that point? Awesome. Finding this black limit is a bit complicated because the red formula is complicated. So we use this idea of comparing terms that add to create a much simpler green formula. Comfortable?
So basically the green formula is like so close to the red formula that you can still use it, but it's not exactly the same.
Super close. Somebody answer this. Somebody answer this. Henry said the red formula is so close to equaling the green formula that it's okay for us just to use the green formula. That's true, but only for a specific reason. Laura?
So it's not about how close it is for individual points, it's just in the long run when we're talking about limits, like how close it's going to get to the same limit. So.
Super close again. We just got to qualify this. So no, 3 points. We just got to be a little bit better. Go, Pierce.
It goes like either up to like infinity or like down, like up to plus infinity or down to negative infinity. The other terms will get so insignificant compared to the bigger terms that it doesn't really matter. So just the big terms are the only thing we need in the expression.
Good job. Okay. Sorry. Get a little excited. Like my markers. Stand back up. Okay. No, really. Hey. Nice. I did that once. Like I got the class so focused. Like really, the level of focus just kept getting higher and higher. And the class is just like on the edge of their seat. Like they're just like so glued to what we're talking about that I timed it perfectly. Like I hit the board, the whole room like went back in their seats like 3 feet. Like it was like this amazing. I still had a video. Like it was like, it's like I had a string and I pull it, and I pull them back. I turn over here. This poor young lady, she's on the floor. Like no joke. Like her books are like everywhere. And she's apologizing. She's like, I'm so sorry. I just startle easily. I'm like, it's my fault. I'm the one who did that. Okay. No, this is what Pierce said. Look. Back to Henry's little summary here. Henry, blue is the same as red, yes?
Yes.
Good. This black limit, perfectly the same as this black limit, because these formulas, blue and red, are identical. Blue is not identical to green really at all. Only if x grows forever. So if you let x get bigger and bigger, the green and the red get closer and closer to being the same. Now you can become very, very positive or very, very negative, doesn't matter. But the green and the red will become closer and closer to equaling each other perfectly as x gets more and more negative or more and more positive. Because we're doing a limit, we're saying, we're pretending that x just never stops growing. So those two formulas, green and red, never stop getting closer and closer to being the same. So we say in the limit they are the same. Did that answer your question?
Yeah.
Good work. Oh, please.
So if the limit had a number, if you only go to a certain number, these rules wouldn't apply.
Say it one more time.
So if like x was getting increasingly closer to like 1, these rules wouldn't apply?
Listen to what she just said. If we're finding the limit as x approaches 1, or x approaches 1,000, we cannot do the comparison.
Only if they're like growing forever.
Perfect.
Okay.
Only if x is becoming more and more positive forever, or x is becoming more and more negative forever. Then the comparison idea is valid. We have to, of course, do the comparison correctly, but this comparison idea here is only valid in those two cases. If we're finding the limit as x approaches 1 trillion, this doesn't apply anymore because x isn't growing forever. Did you hear the difference? Two more, please, Jane.
So remember if that x that was wasn't there, and we just had.
Okay, you got to start one time. I couldn't hear anything.
Sorry.
It's not your fault.
If we didn't have the x over 1 million that was making y negative, what would be the statement?
Oh, I got
Because
you.
it would like make it so that it was
So what you're saying, I think, let me see if I rephrase the question. You tell me if I'm right or wrong. What Jane is wondering is, what if we had done all this work and we'd ended up with a limit that looks like this? The limit, as x approaches negative infinity, of simply 1/4 multiplied by like x, I don't know, cubed over x cubed. Something like that. Now as x becomes increasingly negative, this would stay at 1/4. This would always be 1, and so our limit would be 1/4. Comfortable? The conclusion would be f does have a horizontal asymptote on the left half, and the value of that asymptote is y equal 1/4. 3 points for Jane. Please.
Sorry, I got kind of lost.
You're good.
At the when we were figuring out the negative, like the limit x will get closer to negative infinity, and then like 1/4.
This one here. So you're thinking of a list of x, y values, and you're thinking of the x becoming increasingly negative. Comfortable there? The 1/4 is just going to be 1/4 because there's no x in that yellow box. So just ignore that. It doesn't matter how negative x becomes. this numerator is going to match the denominator perfectly. So that will just always be 1. But then the, so just go after class. So this one here, Ava, as x becomes more negative, this purple becomes more negative because it's the value of x. So that means this whole formula, 1/4 multiplied by 1/4 multiplied by 1 multiplied by a number that just gets more and more negative. As x becomes more and more negative, the Brown formula becomes more and more negative.
So if there's still like a x, if there's still x on top of the equation, it's still going to grow
It'll-
negatively or.
Yeah, it's either going to go negatively or positively, depending on the sign. I wouldn't memorize the fact that there's an x on the top. I would just memorize this process of thinking through like, hey, I'm just going to break it up and just look at each one, each part does. That's safer because we might run into situations where it's something else, but it still might grow. So just learn to kind of break it up in pieces. 2 more.
So just for this case, then had the x been on the bottom, and it would have had hit an asymptote, which just keeps getting to a smaller and smaller value.
Ever hear that? You said, what if it were 1/x? Well, the yellow wouldn't change, the blue wouldn't change, but the 1/x would get closer and closer to 0 as x became more and more negative. Therefore, we would have a horizontal asymptote of y equals 0. It's perfect. 3 points for Jack. Please, Rachel.
I'm just wondering what the difference between the left half horizontal asymptote and the right half horizontal asymptote.
Gotcha. The only difference is, in fact, I don't think they use that word in a book. I use it because I think it helps all of us understand better. But the only difference is, are we thinking of x becoming negative and more negative? Or are we thinking of x being positive and more positive?
So the left hand or left half horizontal asymptotes are getting closer to the negative infinity, on the right hand are getting closer to positive.
Correct. So like as you look at a graph, Rachel, the x is becoming more and more negative means your left hand's going that way, right? That's why I call it that. Does that make sense? 3 more.
Is the conclusion the entire thing on the bottom row, or is it just the...
Gotcha. I think you should have written on your work, we did a lot of writing as we discussed, I think you should have this box written. If you don't write the next line, I'm okay with that. If you just have right here, oh, I can see what's going on now. This is going to negative infinity. But you really should have either this purple or this, we'll call it brown here. One of those two or both should be on your page with the result. And then the therefore thing over here. So, is that your question, Hero?
Yeah.
Cool. 2 more, please.
So, if it does have a left-hand asymptote, then would it be considered wrong if you set the limit of f of x to equal the limit of our simplified version?
Oh, it all depends on what x is approaching.
Yeah. So if it had an asymptote, right?
So say your question one more time, Evan.
So if you had the asymptote of 1/4, right? Would the answer be considered wrong because we set f of x equal to our simplified version, I guess?
So this answer over here was basically saying we would have started with a different f of x. Like the only way we could get this to happen is if f was different in the beginning. The squared term here would have had to have been cubed, and then we would have ended up here. You good there? You've got a great question. I'm struggling to get it. It's not your fault, it's mine. So say it one more time.
So because it's wrong if we have, sorry, I'm trying to say this.
You're doing great.
So it has to, the simplified version is only right of x of 3 over 4x squared. It's only right when x is approaching negative infinity and we have no asymptote, right? So
stop right there for a second. Whether we have a whether we have a horizontal asymptote or not is irrelevant.
Oh, okay.
Yeah, don't
Okay.
tie that together. What's relevant, Evan, is okay, here's f. Here's the formula for f. Those are perfectly identical. If we go find the limit of that formula as x becomes either increasingly negative or positive, we are allowed to say that these two limits are the same. Like they're identical limits, as long as x is becoming increasingly positive or negative. It has nothing to do with what we end up finding the limit to be. Was that your question?
Yeah.
3 more. Solid, cool. So this problem is done. We've found the limit. We know what the meaning of the limit is. We've written that down. There's nothing more to do here. Cool, stop the video.